Tonight we're going to explore a single moment in a quiet room in Cambridge, England, when a small team of astronomers sat in front of a screen in the middle of the night and watched a graph finish drawing itself, and realised that the faint dip in the light they were looking at might, just might, be the smell of an ocean rising off a world 700 trillion miles away. There was no alarm, no siren, no dramatic music, hum of computers, and the pale glow of a monitor, and a line on a chart bending down at a wavelength of light that, on Earth, only living things tend to leave behind. One of them leaned closer. Someone spoke quietly, and for a room, a group of people held in their hands the possibility that they were the first human beings to smell life on another planet. That is where we begin tonight. Not with certainty, not with a headline, with a question and a group of tired scientists who are not sure whether the universe had just answered them or whether the wind had simply rattled the door. Tonight we're going to sit with that graph and that room for a while, because the whole story grows out of it. What we're looking for is called dimethyl sulfide. On Earth, it is the reason the seaside smells the way it does. That briny, sulphurous, almost cabbage tang that hits you when you walk down to the edge of the ocean. The smell that tells some part of your brain, before you have thought about it at all, that this place is alive. That smell is made, for the most part, by things too small to see. Microscopic algae drifting in the sunlit upper layer of the sea, blooming and dying by the trillion, releasing their chemistry into the water and the air. That, tonight, is the molecule at the centre of our story, and the astronomers in Cambridge believe they may have detected it in the atmosphere of planets so far away that its light left before your grandparents were born. Tonight, we're going to follow that chemical all the way from the tide pools of Earth to the sky of another world. The planet is called K2-18b. It orbits a small, dim red star in the constellation Leo, 124 light-years from where you are lying right now. That distance, written out in the units your body understands, is about 729 trillion miles. It is a number so large it stops meaning anything. And around that faraway ember of a star, a world turns that is more than twice the width of Earth and more than 8 times its mass, wrapped in a sky of hydrogen. And possibly, though we will spend the whole night questioning that word possibly, hiding an ocean beneath it hundreds of miles deep, tonight we're going to explore that planet, and that ocean, and that molecule, and the golden telescope that reached across all those trillions of miles to sniff at an alien sky. And we're going to explore something harder than any of those things, which is doubt. Because this is not a story with a clean ending. A story of humanity standing at the threshold of the most important discovery it could ever make, and not being sure, still not being sure, whether it is standing at a door that's opening or simply listening to the wind. If you're watching this in bed tonight, go ahead and turn down your screen brightness, get comfortable, and let's spend the full night inside one of the most extraordinary questions science has ever asked. Now let's begin. To understand what the astronomers found, you first have to understand where they found it, and to do that you have to leave the warm, familiar shape of our own solar system entirely behind. Picture the sun as you know it, a yellow-white star, steady and bright, warming the small rocky worlds close in and throwing its light out past the great gas giants to the cold edges of everything. Now dim it. Take that steady yellow warmth and cool it down until it glows more like an ember than a flame, until it is smaller and redder and quieter, a star with less than half the sun's mass and less than half its width, giving off only about 2% of the sun's light. That is the kind of star K2-18 is. Astronomers call it a red dwarf, and red dwarfs are, by a wide margin, the most common kind of star in the galaxy. When you look up at the night sky, almost none of the stars you can see with your eyes are red dwarfs, because they are too faint to notice, but they are everywhere. The galaxy is full of these small red embers, burning slow and cool and long. K2-18 sits in the constellation Leo, and it is old. astronomers estimate it has been burning for around 2.4 billion years, give or take a few hundred million. For comparison, our own Sun is about 4.6 billion years old, and the Earth beneath you is about 4.5 billion. So this is a younger star than ours, though still ancient by any human measure. Its surface glows at around 5,760 degrees Fahrenheit, cooler than our Sun's roughly 9,900 degrees, and that lower temperature is exactly why it looks red rather than white. Cooler fires glow redder. It is the same reason the low coals in a dying fire look orange, while the hottest part of a flame looks almost blue. Tonight we're going to spend a long time in the light of that red ember, because everything we know about the planet comes from the way it dims and colours that starlight on its way to us. And around that small red star, at a distance of only about 14.8 million miles, moves the world we came here to think about tonight. 14.8 million miles sounds enormous, and it is, but in the arithmetic of star systems it is close. It is closer to its star than Mercury is to our Sun. If K2-18b orbited the Sun at that distance, it would be a scorched and lifeless rock, boiled clean of any air or water, but its star is not the Sun. Its star is dim. And so, orbiting that close to a faint red ember, K2-18b receives roughly the same amount of energy from its star that Earth receives from the Sun. It sits, by that measure, in what astronomers call the habitable zone, the band around a star where the warmth is neither too much nor too little, where water, if there is any, might be able to stay liquid rather than boiling away or freezing solid. By the end of tonight, you will understand why that phrase, the habitable zone, is both the most exciting and the most misleading phrase in this entire story. But hold it gently for now. Just know that this world sits in the warm band, close to a cool star, and that it takes only about 33 Earth days to complete one full orbit. 1 year on K2-18b, one entire trip around its star, is shorter than a single month here. If you lived there, you would be thousands of years old. That dim closeness to a cool star will matter more than you might expect, because it is the whole reason a world this near its Sun is not simply scorched away. The planet itself is a strange thing, and to feel how strange, you should hold its size in your mind. K2-18b is about 2.6 times the width of Earth. If you could somehow set it down next to our world, it would loom over it, wider by more than double, and it is heavy, about 8.5 times the mass of the Earth. That combination, more than twice as wide but more than 8 times as heavy, tells scientists something important about what it is made of, and it is here that the mystery starts to deepen. If K2-18b were a scaled-up ball of rock and iron like the Earth, it would be far heavier than it is for its size, and if it were a puffed-up ball of gas like Neptune, it would be far lighter. It sits in between. Its density falls squarely between rocky Earth and gassy Neptune, which tells astronomers that it is probably neither. It is likely something layered and in between. A core of rock perhaps wrapped in mantles of high-pressure ice, the kind of exotic ice that forms only under crushing pressure and can stay solid even when it is hot. And around all of that, an envelope of hydrogen and helium gas, thick and light, giving the world its size without adding much to its weight. Let me take you down into that layered interior for a moment, because it is one of the strangest places imaginable, and picturing it may be a soothing thing to do in the dark. At the very centre, most models agree there is likely a core of rock and metal, something not unlike the heart of the Earth. But above that core the resemblance to home ends. Under the crushing pressures inside a world this heavy, water does not behave the way it does in your kitchen. It can be squeezed into forms of ice that stay solid even at temperatures that would boil an ordinary pot dry, exotic high-pressure ices of the kind thought to fill the deep interiors of Uranus and Neptune. So above the rocky core there may be a thick mantle of these strange hot ices, and above that, in the most hopeful picture, a layer of liquid water, an ocean hundreds of miles deep. And above the ocean, at last, the vast light envelope of hydrogen and helium gas that gives the planet its size. Core, then ice, then perhaps sea, then sky. A one under the weight of everything above it. To descend through it would be to pass from gas into water, into ice, into rock, through pressures that climb without mercy the whole way down. And the star it orbits is not perfectly calm, which matters for anything that might live there. K2-18 is a red dwarf, and red dwarfs, though they burn slow and long, are prone to flares, sudden bursts of radiation that can wash over their close-orbiting planets. Astronomers have measured a steady output of X-ray and ultraviolet radiation from the star and have caught it flaring, several distinct flares recorded in the observations. Over the long span of geological time, that radiation can strip away a planet's atmosphere, eroding the very sky whose chemistry we're trying to read. Whether K2-18b has held onto a stable, life-friendly climate through billions of years of this, or whether its star has slowly worn at it, is another of the open questions that hangs over the whole hopeful picture. A calm surface for life is not something you can simply assume around a small, flaring star. Astronomers have a name for this kind of world. They call it a sub-Neptune, or sometimes a mini-Neptune. Smaller than Neptune, larger than Earth, and here is the part that should make you sit up, or rather, since it is late, the part that should make you settle deeper into your pillow with a small, quiet sense of wonder. Sub-Neptunes are the single most common type of planet in the entire galaxy. When astronomers count up all the worlds they have found circling other stars, this in-between size, bigger than Earth and smaller than Neptune, shows up more than any other. It is the galaxy's favourite kind of planet. By the end of tonight, you will see why that ordinariness makes the whole story stranger, not less strange, and we do not have one. Nowhere in our solar system is there a world like this. We have small rocky planets close to the sun, and giant gassy planets far out, and nothing at all in the middle. So the most common kind of world in the galaxy is a kind of world we have never once seen up close, never sent a probe to, never photographed from orbit. K2-18b is one of these. It is in that sense more representative of the galaxy than the Earth is, and no one expects the most ordinary kind of planet in the universe to be the one that hides the biggest secret. But that is exactly the strange gift of this story. Let me tell you how it was found, because the finding was quiet too. In 2015, NASA's Kepler Space Telescope, in the extended phase of its mission that astronomers called K2, was staring patiently at a patch of sky. Kepler did one thing, and it did it with extraordinary devotion. It watched stars for tiny dips in their brightness. When a planet passes in front of its star, as seen from our point of view, it blocks a minuscule fraction of that star's light. Not enough for any human eye to notice, but enough for a sensitive instrument to measure if it watches long enough and carefully enough, and every 32.94 days, like clockwork, K2-18's light dimmed by a tiny amount and then recovered. Something was passing in front of it. A world was crossing the face of its star for and over on a perfect schedule. That regular little shadow is how K2-18b announced itself to us. Not with a flare or a signal, but with a whisper of dimming, repeated with the patience of orbital mechanics. There is a gentleness to that method that I want you to feel, because it is so different from the way we usually imagine discovery. There was no moment of triumph, no astronomer crying out at an eyepiece. There was a star, and a graph of its brightness measured over many nights, and in that graph a tiny valley that returned again and again on a fixed schedule. A machine noticed it before any person did. The planet did not reveal itself so much as it was inferred, patiently, from arithmetic. Every 32.94 days, the light dipped by a fraction of a percent, and from the depth of that dip, astronomers could work out how large the planet must be, and from the timing they could work out how far it orbited, and from years of watching a small handful of red stars, a new world quietly took its place in the catalogue of things we know exist. For a while, that was almost all we knew. A size, an orbit, a temperature estimated from those. But then, In 2019, before Webb had even launched, the older Hubble Space Telescope turned its attention to K2-18b and reported something that made astronomers sit up. In the filtered starlight passing through the planet's atmosphere, two independent teams found signs of water vapour, and they announced, cautiously, that this was the first detection of water in the atmosphere of a planet in the habitable zone of its star. Water in the air of a world that sat in the warm band at a distance from its star where liquid water might be possible. It was a genuine milestone, and it put K2-18b on the map as a world worth watching. Later work would complicate even that, suggesting that some of what looked like water might actually have been methane leaving its own marks in the spectrum, a reminder of how easily one molecule can be mistaken for another when the signal is faint. But the water vapour announcement was the moment K2-18b stopped being just another entry in a database and became a place, a specific world that scientists began to dream about. Tonight we're going to trace how that dream grew and how later it learned to doubt itself. There may even be more than one world in that system. Back in 2017, astronomers studying the tiny gravitational tug of planets on their star reported hints of a second world, which they called K2-18c, a planet of perhaps 7.5 times Earth's mass on a tighter, faster orbit of around 9 days. But that second world has never been confirmed. A later analysis using different instruments disputed the detection, and K2-18c remains one of those maybe planets that hovers at the edge of the catalogue, neither confirmed nor ruled out. It is a small reminder that even the basic census of a star system, how many worlds it holds, can be a matter of live debate. We are still learning to count what is there. That is worth sitting with for a moment, because it tells you something about how humble the whole enterprise is. We do not, for the most part, see these planets. We cannot photograph K2-18b. It is far too small and far too dim and far too close to the glare of its star for any telescope to take its picture. Everything we know about it, everything we will talk about tonight, comes from indirect measurement, from the timing of shadows, from the bending of starlight, from the faint fingerprints that molecules leave in the colours of light. We are reading a world we cannot see, the way you might come to know the shape of a room in the dark by the sounds it makes, and the way the air moves. Tonight we're going to keep coming back to that humility, because it is the ground everything stands on. We have never seen this planet, we have only read it. So what would it actually be like, this world we have read but never seen? Let yourself drift toward it for a moment. Imagine you could stand somewhere on K2-18b if there were anywhere to stand. Under the leading model, and we will come to the arguments over that model soon, there may be no solid ground at all. Just an ocean, worldwide, unbroken, stretching in every direction with no shore and no island and no continent to interrupt it. A single ocean wrapped around an entire planet, and beneath your feet, if you could float on its surface, that water might go down not 2 miles the way Earth's oceans average, but 140 miles, or 200, or 350 miles down into darkness and pressure before it even reached whatever lies beneath. And above you, the sky would not be blue. Blue sky is a trick of Earth's air, of nitrogen and oxygen scattering the sun's light. K2-18b's air is mostly hydrogen, and hydrogen scatters light differently. So the sky would be some other colour, dimmer, stranger, and hanging in it would be that red dwarf star, swollen and dim, taking up a noticeably larger slice of the sky than our sun does, but glowing with a soft orange-red light more like the colour of a dying campfire than the fierce white of noon. It would not hurt to look at. It would sit there, a great dim ember, and its light would fall across an endless dark sea. The air would kill you, of course, if you tried to breathe it. Hydrogen, with carbon dioxide and methane mixed in, sweet-smelling perhaps in some faint way, and utterly without the oxygen your body demands. And the pressure would be crushing, tens or even hundreds of times the pressure you feel at sea level here, the way you would feel it if you sank hundreds of feet down into one of Earth's own oceans. This is not a gentle place. It is not somewhere you could ever go. And yet, if the more hopeful reading of the data is right, it might be somewhere that something lives. Gravity there would be heavier than home. On the surface of K2-18b, if there were a surface, you would weigh noticeably more. A person who weighs 180 pounds standing in their bathroom on Earth would weigh around 228 pounds standing on K2-18b. Every step would be an effort. Your own body would feel like a burden you were carrying. The world would press down on you the way a heavy blanket presses down now, except everywhere, and without relief. And there may be no day and no night in the way you know them. K2-18b orbits so close to its star that it may be locked in place, always showing the same face to that red ember, the way our moon always shows the same face to us. If that is true, then one hemisphere of the planet lives in a permanent dim day, and the other in a permanent night. And the only place where the temperatures might be gentle enough for anything delicate to survive would be the twilight band between them, the endless ring of perpetual dawn that runs around the whole world where day meets night. Imagine that. A place where the sun never rises and never sets, where it simply hangs low and red and unmoving on the horizon forever, and a dark ocean laps beneath it, and nothing ever changes. If there is life there, it lives in that twilight, in a world without days. No one expects a living world to look like this, a shoreless sea under a sun that never moves, and yet this may be the most common shape a habitable world can take. By the end of tonight, you will see how much of what I've just described is genuinely uncertain, how much of it is a model rather than a fact, how many careful scientists would gently push back on nearly every image I have painted. The ocean might not be there at all. The whole planet might be a different kind of thing entirely. But before we take it apart, I wanted you to see it whole, the way its discoverers first dared to imagine it. By the end of tonight, you may hold this ocean more loosely than you do now, and that loosening is itself part of the story. A dim red sun, a world-wrapping sea, a hydrogen sky, and somewhere in that dark water maybe, the same kind of thing that makes the smell of the ocean here on Earth. Because here is the number that started it all. On Earth, dimethyl sulfide exists in the atmosphere at a concentration below 1 part per billion. It is a trace of a trace, a whisper of the sea's chemistry lifted into the air. On K2-18b, the astronomers in Cambridge estimated that dimethyl sulfide might be present at around 10 parts per million. That is more than 10,000 times higher than anything ever measured in Earth's atmosphere. If that reading were true and biological, it would mean the ocean of K2-18b was not just alive, but overwhelmingly, extravagantly alive. It would mean a sea so thick with living things that the whole planet was essentially exhaling, breathing its biology out into a hydrogen sky at a scale that dwarfs anything our own living world produces. No one expects a first sign of alien life to arrive as a modest, ambiguous trace. And yet, if this reading is real, it is not modest at all. It is a shout. But we're getting ahead of ourselves, and this is a night for slowing down. To understand whether that shout is real, or whether it is the wind, we have to understand the golden instrument that heard it. And so, we leave the dark ocean of K2-18b for a while, and we travel back across those 700 trillion miles, back toward home, to a point in space about 1 million miles from the Earth, where a machine the size of a tennis court floats in perpetual cold, staring outward, listening to the light. Tonight we're going to spend a while with that machine, because you cannot judge what it found without understanding what it is. The James Webb Space Telescope launched on Christmas Day in 2021. Think about that timing for a moment, because there is something quietly moving in it. On the morning that much of the world was waking to give gifts, a rocket lifted off from a launch pad in Kourou, in French Guiana, on the northeastern shoulder of South America, carrying into the sky the most expensive and most ambitious scientific instrument our species had ever built. It had taken more than 2 decades to design and construct, and cost around $10 billion, and involved the space agencies of the United States, Europe, and Canada working together across all those years. And for its entire long history on the ground, It had never been tested as a whole in the conditions it was built for because those conditions do not exist on Earth. It had to work the first time in space, or not at all. No one expects a machine that fragile and that complicated to unfold flawlessly on the first and only try, 1,000,000 miles from any hand that could fix it, and yet it did. It did not go to orbit around the Earth the way the older Hubble telescope does. It went much farther, to a special place about 1,000,000 miles away, on the far side of the Earth from the Sun, a point astronomers call the second Lagrange point, or simply L2. It is a place of gravitational balance, where the pull of the Earth and the pull of the Sun combine in just the right way that a spacecraft placed there tends to stay there, drifting along with the Earth as we both circle the Sun, keeping its distance, holding its station. From L2, the telescope can keep its back permanently turned to the Sun, the Earth, and the Moon, all at once. All three of them huddle behind it in the same patch of sky, so that its great shield can block their light and heat, and let the instruments stare out into the cold and the dark undisturbed. And it must be cold. This is the part that surprises people. Webb is an infrared telescope. It sees not the visible light your eyes use, but the longer, redder wavelengths of infrared, the light of heat, and to see the faint infrared glow of distant worlds. It must not be glowing itself. Anything warm gives off infrared light. Your body does. This room does. And a warm telescope would be blinded by its own heat, drowned in its own glow, the way you cannot see a candle if you're staring into the sun. So Webb had to be made cold. Bitterly, almost impossibly cold. Its instruments are chilled to around 387 degrees below 0 Fahrenheit, which is only a little above the coldest temperature that is physically possible anywhere in the universe. To keep them that cold, the telescope unfurled, after launch, an enormous 5-layer sunshield about the size of a tennis court, 69 feet long and 46 feet wide, each layer thinner than a hair, spreading out one after another to hold back the warmth of the sun. The heart of it is the mirror, and the mirror is beautiful. It is 21.3 feet across, made not of one piece but of 18 separate hexagonal segments, fitted together into a single great honeycomb, and every one of those segments is coated in a whisper-thin layer of pure gold, only about 100 nanometers thick, which is something like 1,000 times thinner than a human hair. Gold, because gold reflects infrared light better than almost anything else. That gold honeycomb catching the faint infrared glow of the distant universe is the eye that looked at K2-18b. And it is large. Webb's mirror is more than 2.5 times the width of Hubble's older mirror, which means it gathers far more light, which means it can see fainter things and read finer detail than any space telescope before it. The whole machine weighs about 14,300 pounds, and it was folded up like origami to fit inside its rocket, then unfolded itself over the weeks after launch in a long, tense, precisely choreographed sequence of hundreds of steps, any one of which, had it failed, might have crippled the mission. None of them failed. The launch itself was so precise, so gentle, that the telescope used far less fuel than expected getting into position, which means that instead of the 10 years of life it was designed for, it may keep working for 20. It reached its distant post about a month after launch in late January of 2022, and by the middle of that year it had opened its golden eye and begun to work. And one of the first things people wanted to point it at was the atmospheres of other worlds. Hold in your mind for a moment just how faint the thing is that this machine was built to catch. The light that Webb gathers from a planet like K2-18b is starlight that left a dim red star 124 years ago, crossed 700 trillion miles of empty space, grazed through a thin sliver of alien atmosphere on its way, and arrived at last, spread impossibly thin, at the golden mirror. By the time it lands, it is a whisper of a whisper, a scattering of individual particles of light so few that they must be counted almost one by one. To catch them, the mirror must be large, to gather as many as possible, and it must be cold, so that its own warmth does not drown them out, and it must be steady, holding its aim on a single faint star for hours without wavering by more than a hair. The gold on its surface is thinner than you can imagine, only about 100 nanometers, a coating so fine it would take 1,000 of them stacked together to match the width of a single human hair. And yet that thin gold skin is what reflects the faint infrared light of distant worlds into the waiting instruments. Everything about the machine is an answer to the same problem, which is that the signal it hunts is almost nothing at all, and it must be built to notice almost nothing. Now, how do you read the air of a planet you cannot even see? This is the part of the story that I find quietly astonishing, and I want to walk through it slowly, because once you understand it, you will never look at starlight the same way again. Remember that K2-18b passes in front of its star every 33 days, from our point of view. When it does, it blocks a tiny fraction of the starlight. But here is the thing. The planet is not a solid disk. It is a solid world wrapped in a shell of atmosphere, and that shell of atmosphere is not opaque. When the planet crosses in front of the star, most of the star's light goes around it into space, but a thin sliver of that light passes through the very edge of the planet's atmosphere on its way to us. It grazes the top of the alien sky, filtering through perhaps 100 miles of gas, before continuing across all those trillions of miles to fall, at last, on the golden mirror at L2, and that light is changed by its passage. Because molecules are picky about light. Every kind of molecule, methane, carbon dioxide, water, dimethyl sulfide, absorbs light at its own particular set of wavelengths and lets the rest pass. So when starlight filters through an atmosphere, the molecules in that atmosphere each take a small bite out of it, removing their own specific colours, leaving little gaps in the spectrum, little missing wavelengths where the light was swallowed on its way through. When astronomers compare the star's light during a transit, when it has passed through the planet's air, against the star's light at other times, when it has not, they can see which colours went missing, and from the pattern of missing colours, they can read which molecules were there to take them. By the end of tonight, this quiet trick of reading shadows and colour will feel almost ordinary to you, and I want you to remember, when it does, how extraordinary it truly is. This technique is called transmission spectroscopy, and it is one of the most extraordinary things human beings have ever learned to do. Think about what it actually is. You are standing 700 trillion miles away from a planet you cannot see, and by watching how the light of its star dims and changes as the planet crosses in front of it, you're reading the chemistry of its atmosphere, molecule by molecule, from the shadows those molecules cast in colour. The entire mass of gas you are measuring is lighter than a mountain, spread thin around a world you will never touch, and you are identifying it by name. There is an image I keep returning to when I try to feel the difficulty of this. Imagine trying to read the ingredients list printed on the side of a candle, not by picking it up, but by standing 3/4 of a mile away and watching its flame, while every so often someone briefly waves a sheet of tinted glass in front of it, and you have to work out what the candle is made of from the way the flame's colour flickers through the glass. And then imagine doing all of that in colours of light your eyes cannot even see. That is roughly the scale of the thing that Webb does when it reads an alien sky. It should not be possible. It is barely possible, and it works. No one expects to read the ingredients of a candle from 3/4 of a mile away in colours they cannot see. And yet that, in essence, is what the golden mirror does every time it watches a planet cross its star. Webb does it with several instruments, each tuned to a different band of infrared light, and together they build up an almost complete fingerprint of an atmosphere. There is an instrument that reads the shorter infrared wavelengths, and another that reads the middle band, and another that reaches out into the longer mid-infrared wavelengths where certain molecules leave their clearest marks. The reason more than one instrument matters will become the heart of the argument later tonight, so hold on to it. Different molecules show themselves at different wavelengths. Methane leaves its fingerprints in a couple of places, one around 3 micrometers and one further out, carbon dioxide has a strong clear mark of its own, and dimethyl sulfide, the molecule at the centre of everything, leaves its subtle traces spread across several wavelengths, including some out in the mid-infrared, which is exactly why the team eventually brought in the instrument that reads that longer, harder band of light to go looking specifically for it. By the end of tonight, the choice of which instrument reads which wavelength will turn out to be near the centre of the whole argument, so let it settle in gently now. The first serious look at K2-18b with Webb came in January of 2023. The telescope watched the planet cross its star, and for a little over 5 hours it gathered the filtered light, catching the faint colours that had passed through that hydrogen sky. And here is a measure of how good Webb is. The older Hubble telescope had also looked at K2-18b years earlier, and it had taken Hubble 8 separate transits, gathered across multiple years, to build up a spectrum with any real detail. Webb matched and exceeded that with just 2 transits, each only a handful of hours long. 2 afternoons of watching, essentially, against years of patient work by the older instrument. That is the leap the golden mirror represents. It gathers so much more light, across so much more of the spectrum, that it can hear in an afternoon what its predecessor strained for years to catch. And by the time Webb turned toward K2-18b, it had already proven that it could do this at all, on a world where the stakes were lower and the answer clearer. Back in the summer of 2022, in its very first months of science, Webb had looked at a planet called WASP-39b, a puffed-up hot giant orbiting a star some 700 light-years away. WASP-39b is nobody's idea of a home. It is scorching, bloated, uninhabitable, a great ball of hot gas hugging its star. But precisely because it is so large and so hot, its atmosphere is easy to read, and Webb read it in extraordinary detail. It found carbon dioxide cleanly and unambiguously, the first time that gas had ever been detected beyond doubt in the atmosphere of a planet around another star. And it found more. Sodium and potassium and water and carbon monoxide and even sulfur dioxide. A whole chemical inventory of a world no human eye will ever see, written out in the shadows that molecules cast in starlight. No one predicts, standing on the Earth, that we would ever hold a detailed chemical portrait of a planet 700 light-years away, and yet there it was. WASP-39b was the proof of concept, the trial run. It showed that the method worked, that the golden mirror really could name the gases of an alien sky. And so, when Webb turned its attention to a far harder target, a small temperate world where the answer might actually matter, the astronomers already knew the tool in their hands was real. But hearing is not the same as understanding, and this is where the human part of the work begins. When the light comes down from L2, it is not a neat list of molecules. It is a noisy, imperfect graph, a scatter of measurements of how much light came through at each wavelength, riddled with the ordinary uncertainties of any real measurement. To turn that graph into a statement about what the atmosphere contains, scientists run a process called atmospheric retrieval. And retrieval is not a simple reading. It is a kind of reasoning. You take the observed graph and you ask a computer to imagine millions of possible atmospheres, each with a different mixture of gases at different amounts and temperatures, and for each imagined atmosphere you calculate what its spectrum would look like, and you compare that to what you actually saw, and you keep the mixtures that fit and throw away the ones that do not. And slowly you build up a picture of which combinations of molecules could plausibly have produced the light you caught. It is done with the mathematics of probability, weighing one explanation against another, always in terms of likelihood rather than certainty. And the scientist most associated with pioneering this kind of reasoning for the atmospheres of distant worlds is a man named Nikku Madhusudhan of the University of Cambridge, and it was his team that sat in that quiet room and watched the graph draw itself. Madhusudhan spent his career developing the tools to read these faint alien spectra, to pull a whisper of chemistry out of a noisy measurement. So when the retrieval on K2-18b's light came back, and it seemed to show something unexpected, he was not a man inclined to ignore it, but he was also, it must be said, a man who knew exactly how easy it is to fool yourself with a noisy graph. And that tension between the thrill of the signal and the fear of the mirage runs through everything that came next. No one expects the discoverer to be his own fiercest doubter, but in the best science that is exactly what happens, and it is what happened here. Because two transits, each one a handful of hours. From that, and from the patient reasoning of retrieval, the team read the chemical composition of an atmosphere on a world more than 700 trillion miles away, an atmosphere of gas lighter than a mountain, wrapped around a planet only about 20,000 miles across, orbiting a dim red star you cannot see with your eyes. Whatever you come to believe about what they found there, the finding itself, the sheer fact that human beings can now do this at all, is one of the quietly astonishing achievements of our time. 400 years ago we were arguing about whether the Earth went around the Sun. Tonight a golden mirror a million miles away reads the exhalations of a planet in another star's light. And no one predicts, when they first learn how young this ability is, just how far it has already reached. So let us turn now to what they read, and to understand why it caused such a stir, we have to slow down and really look at this one small molecule, dimethyl sulfide, and understand why. Of all the chemicals in the universe, this particular one made a room full of careful scientists lean toward their screens. Tonight we're going to give this one small molecule the attention it deserves, because the entire question of whether we have found life may rest on it. Its formula is simple. 2 methyl groups, each a carbon atom with 3 hydrogens, joined to a single sulfur atom in the middle. Written down, it is CH3SCCH3. At room temperature on Earth, it is a colourless liquid, and it has a smell that anyone who has ever stood at the edge of the sea already knows in their body, even if they have never known its name. That sulphurous, briny, faintly cabbage-like tang that rises off tide pools and harbours and open water. When people say they love the smell of the ocean, a great deal of what they are loving is dimethyl sulfide. It is one of the main things that makes sea air smell like sea air. And on Earth that smell has a source, and the source is alive. In the sunlit upper layer of the oceans drift countless microscopic organisms, the phytoplankton, single-celled algae so small that a spoonful of seawater can hold more of them than there are people in a city. They are the invisible forest of the sea, and like the forests on land, they are the base of nearly everything, feeding the whole ocean food chain from below. Many of these tiny algae make a particular compound inside their cells, and when they die, or when they are eaten, or when they are stressed, that compound breaks down, and one of the things it breaks down into is dimethyl sulfide. Certain ocean bacteria help along the way, taking the algae's chemistry apart and releasing the sulphurous gas, and then the gas ventilates up out of the water and into the sky. About 27 million tons of sulphur's worth of it every year, drifting into the air over all the world's oceans. So on Earth, dimethyl sulfide is a signature of life in the most direct sense. It is, as far as we know, made overwhelmingly by living things and almost not at all by anything else. No volcano makes much of it. No ordinary chemistry of rock and water and air produces it in any quantity. It comes from the algae and from the bacteria that feed on them, and that is nearly the whole story on this planet. Which is exactly why astrobiologists, the scientists who think about how we might recognize life on other worlds, had for years kept dimethyl sulfide on their short list of what they call biosignatures. A biosignature is a fingerprint of life. A thing that, if you found it in the atmosphere of another planet, would make you think that something there might be alive. And dimethyl sulfide, the smell of the living sea, seemed like a wonderful candidate. If you could smell it across the stars, the reasoning went, you might be smelling life. This is a good moment to introduce the idea that gave K2-18b its whole hopeful frame, because it did not come from nowhere. A few years before the Webb data arrived, Nikku Madhusudhan, and two colleagues at Cambridge had proposed a new class of possibly habitable world, and they gave it a name by stitching two words together: hydrogen and ocean. They called them Hycean worlds. The idea was this. We had always imagined habitable planets as small rocky worlds with thin airs like Earth's, sitting in a narrow warm band around their stars. But what if a larger world, wrapped in a thick hydrogen atmosphere, could hold a liquid ocean beneath that sky even further out from its star, kept warm by the greenhouse blanketing of all the hydrogen? Such a world could be habitable, they argued, in orbits that the old Earth-focused thinking had written off as too cold. The hydrogen sky would trap the warmth, and the ocean beneath could stay liquid. And life, if it were the kind of life that could breathe hydrogen instead of oxygen, might drift in that sea. The original proposal even suggested such worlds might remain habitable at the boundary between their atmosphere and ocean, up to temperatures well above the boiling point of water at sea level here, because the crushing pressure would keep the water liquid even when it was hot. It was, in a sense, an argument for widening the definition of a living world, for imagining that life could take shapes and breathe gases quite different from our own. And that argument did not come from Madhusudhan alone. He had studied, years earlier, under a scientist named Sarah Seeger, one of the founders of the whole field of reading exoplanet atmospheres, a woman who had spent her career thinking about how we might recognize life on worlds utterly unlike Earth. It was Seeger, among others, who had explored the idea that life on a hydrogen world might breathe hydrogen the way we breathe oxygen, broadening the whole notion of what living might mean beyond the single example we have. So when the Webb data came in, Madhusudhan was not looking at K2-18b as a blank slate. He was looking at it through the lens of the Hycean idea, as a possible example of exactly the kind of world he and Seeger and others had spent years imagining. That lens is part of what made the sulfur signal so electric to him, and it is also, his critics would gently point out, part of what a careful skeptic has to watch for. When you have imagined a certain kind of world, you are primed to see it. We will have to weigh that, honestly, on both sides of the scale. By the end of tonight, you will see how that reasoning, so clean and so appealing, ran into trouble from a direction almost no one was watching. The gas even plays a role in Earth's weather, in a way that ties the smallest living things to the largest patterns of the sky. When dimethyl sulfide rises off the ocean and into the air, it gets chemically changed and helps form the tiny particles around which cloud droplets condense. More of the gas can mean more of these particles, which can mean more clouds, which reflect more sunlight back to space, which cools the planet slightly. Some scientists have proposed that this forms a kind of loop, a faint thermostat connecting the algae in the sea to the brightness of the clouds and the temperature of the whole world. Whether that loop truly regulates Earth's climate is itself debated, but the picture it paints is a beautiful one. The exhalation of invisible ocean algae, drifting up to help make the clouds, life reaching up to touch the sky. Sit for a moment with the sheer difference in scale that this involves, because it is one of the quietly staggering things in the whole story. The phytoplankton that make this molecule are microscopic. A single cell is a few millionths of an inch across, far too small for your eye to resolve, so small that a single drop of seawater can hold thousands of them. Individually, they are nothing, invisible, uncountable specks. And yet their collective breathing, the sum of all those tiny exhalations across the entire surface of the world's oceans, produces a chemical trace in the atmosphere that, in principle, could be detected across the gulf between the stars. The smallest living things on Earth, gathered by the uncountable trillion, leave a mark large enough to read from another solar system. That is the scale of the thing the Cambridge team was reaching for. Not a whale, not a forest, not a city, but algae too small to see, and yet loud enough, in their multitudes, to whisper across 124 light-years. If the same is true on K2-18b, then what Webb may have brushed against is not a creature, but a chorus, the summed breath of a whole ocean's worth of the smallest living things rising into an alien sky. Now, carry all of that up to K2-18b. In the September of 2023, Madhusudhan's team published their first Webb results in a paper with the careful, cautious title, Carbon-Bearing Molecules in a Possible Hycean Atmosphere. Notice that word? Possible. It was there from the very start. What they reported clearly with real confidence was the detection of methane and carbon dioxide in the planet's atmosphere. Those two they were sure of. And then, much more quietly, much more tentatively, they noted a faint hint of something else in the data. A whisper at the wavelengths where dimethyl sulfide would show itself. They did not claim to have found it. They were explicit that they had not. They called it a possible signal, something that would need much more work to confirm or dismiss. It was a footnote to the methane and the carbon dioxide, not a headline. But the world does not read footnotes the way scientists write them. The moment the words dimethyl sulfide and habitable zone exoplanet appeared in the same paper, the possibility caught fire in the public imagination, and you can understand why. Here, in one place, were several things at once. A planet in the habitable zone of its star, methane and carbon dioxide together, which on a world with an ocean might be a sign of the kind of chemistry that life stirs up. An absence of another gas, ammonia, which was itself intriguing, because in a hydrogen atmosphere sitting over a liquid water ocean, ammonia would be expected to dissolve down into the water and vanish from the air, so its absence was gently consistent with the idea of a sea beneath the sky. And now, faintly at the very edge of the data, the possible smell of the ocean itself. No single one of these things proved anything, but together, laid side by side, they formed a picture, a circumstantial case, a story that pointed, however softly, toward the possibility of a living world. No one predicts that a footnote in a careful paper will become a headline around the world, but the words dimethyl sulfide once spoken could not be unspoken. And then, in the April of 2025, the team came back with more. They had used Webb's mid-infrared instrument, the one that reads the longer wavelengths, specifically to go hunting in the part of the spectrum where dimethyl sulfide leaves clearer marks. For nearly 6 hours in the April of 2024, the Golden Mirror had gathered the mid-infrared light of K2-18b, and when the team ran their retrieval on that new data, they reported that they now saw independent evidence for dimethyl sulfide, or for its very close chemical cousin, a molecule called dimethyl disulfide, which is built the same way but with 2 sulfur atoms linked in the middle instead of 1. They could not tell the two apart, they said honestly, because their spectral fingerprints overlap. But one or the other seemed to be there, at that same startling abundance, around 10 parts per million or more. Madhusudhan chose his words with care, and it is worth hearing them, because they capture the exact emotional temperature of the moment. A Hycean world with an ocean teeming with life, he said, best fits our data, best fits, not proven by. And elsewhere he said, however you put it, we are seeing new chemical processes on a planet that could be habitable. Could be. New chemical processes. He called the moment profound, and he was careful, again and again, not to say the word that everyone wanted him to say. He did not say they had found life. He said the data was most easily explained for now by a world that had it. There is a discipline in that restraint that I find genuinely moving. To hold in your hands the most exciting result of your career, the possible smell of an alien ocean, and to keep saying out loud, we do not know yet, this could be something else. We need more. Tonight we're going to try to hold that same discipline ourselves, the excitement and the caution at once, the way he did. Because here is the thing about that 10 parts per million. It is a staggering number, and its very size cuts both ways. On the one hand, if it is real and biological, it means life on an overwhelming scale, a sea so productive that it makes Earth's entire biosphere look faint. On the other hand, that same enormous size is exactly what made many scientists uneasy. Why would there be 10,000 times more of this gas on K2-18b than on Earth? Earth's oceans are full of life, packed with the algae that make this very molecule, and even so, Earth's atmosphere holds less than a part per billion of it. To get to 10 parts per million, you would need either a biosphere far more productive than anything on Earth, which is a large thing to assume, or you would need some reason the gas builds up on K2-18b in a way it never can here. And there is such a reason, and it matters, so hold on to it. On Earth, dimethyl sulfide does not last long in the air. Our atmosphere is full of oxygen and, high up, of ozone and of reactive molecules that tear the gas apart within a day or two of its release. It is made constantly and destroyed constantly, and the balance sits low. But K2-18b's atmosphere is not like ours. It is a reducing atmosphere rich in hydrogen, with no free oxygen and none of the aggressive chemistry that scrubs the gas from Earth's sky. In that kind of air, dimethyl sulfide might survive much longer before being broken down, which means it could build up to far higher levels even if it were being produced at a modest rate. So the huge concentration, 10 parts per million, does not necessarily require an impossibly enormous biosphere. It might just require an atmosphere that lets the gas linger. This is a genuinely important point, and a fair one, and it is one of the strongest cards in the hopeful hand. But that same fact, that the gas can build up and linger in a hydrogen sky, is also a door through which the doubt walks in. Because if a hydrogen-rich atmosphere lets biological dimethyl sulfide accumulate, it will also let any non-biological dimethyl sulfide accumulate, and whether such a thing, dimethyl sulfide made without life, could exist at all, was about to become the question on which this entire story turns. By the end of tonight, that single door will have opened wide. Let yourself rest here for a moment before we go further, because we have arrived at the true heart of it. Everything so far has been the setup, a dim red star, a world-wrapping sea beneath a hydrogen sky, a golden mirror a million miles away, reading the shadows of molecules in filtered light, a careful team, a startling signal, the possible smell of an alien ocean at concentrations that beggar belief. If the story ended here, it would be a triumph, unambiguous and clean, the moment humanity smelled life among the stars. But the story does not end here. It is precisely at this moment, at the peak of the excitement, that the ground begins to move, and the rest of tonight is the story of that moving ground. It is a harder story than the first one, and in some ways a more honest and more beautiful one. It is the story of how science, at its best, refuses to let itself believe the thing it most wants to be true. Tonight we're going to walk through that refusal slowly, because it is, in its own quiet way, as beautiful as the ocean we started with. To feel the argument, you first need to understand a single idea, and it is the idea of sigma. When scientists want to know whether a signal in their data is real, or whether it is just noise, they do not simply look and decide. They calculate the odds. They ask, if there were actually nothing there, if the atmosphere held none of this molecule at all, how likely is it that random noise alone would have produced a bump in the data as large as the one we see? And they express that likelihood in units they call sigma. The higher the sigma, the less likely it is that mere noise fooled them. A result at 1 sigma is weak, the kind of bump that random noise coughs up all the time. A result at 3 sigma is more interesting. At 3 sigma there is only about a 3 in 1,000 chance that noise alone produced it. Physicists call 3 sigma evidence. It is worth paying attention to. But it is not enough to be sure. To be sure, in the strict tradition of physics, you want 5 sigma. At 5 sigma, the odds that noise faked the result drop to less than 1 in 3 million. That is the standard the physicists held themselves to when they announced the discovery of the Higgs boson, the particle they had chased for half a century, and they would not say they had found it until the odds against a fluke were more than 1,000,000 to 1. That is the standard the gravitational wave astronomers met when they first heard 2 black holes collide, waiting for a signal clean enough that no reasonable person could call it noise. 5 sigma is what the word discovery is supposed to mean. Below that, you are allowed to be interested, even excited, but you're not allowed to be certain, and you're certainly not allowed to tell the world you have found something new. Now hold that scale in your mind and look again at K2-18b. The April 2025 detection of dimethyl sulfide, the one from the mid-infrared instrument, came in at somewhere between 2.9 and 3.2 sigma, just around that 3 sigma line. Evidence in the language of physics, but nowhere near discovery. A signal with something like a few in 1,000 chance of being a fluke, which sounds reassuring until you remember how many wavelengths, and how many possible molecules and how many choices go into the analysis, each of which is another chance for a fluke to slip through. 3 sigma is a real result, but 3 sigma has been wrong before, many times, in the history of science. 3 sigma is exactly the range where careful people have fooled themselves for centuries, and no one expects the first detection of life beyond Earth to be announced at 3 sigma. The weight of the claim demands more. No one predicts when they read the exciting headline that the number underneath it is so far from the standard that physics reserves for the word discovery. And then it got harder, because other scientists began to reanalyze the very same data, and they did not all find the same thing. This is one of the most important and least understood parts of the whole story, and it is worth going slowly. When a team like Madhusudhan's publishes a result, they also, in the best tradition of science, make their data available, so that anyone else can check their work. And several other teams did exactly that. They took the same raw measurements from Webb, the same photons that had fallen on the same golden mirror, and they ran them through their own analysis, their own choices about how to clean up the data and how to model the atmosphere, and they asked the same question: is there dimethyl sulfide here? And they came back with answers that range from a much weaker signal to no real signal at all. In the July of 2025, a team led by a scientist named Renyu Hu at NASA's Jet Propulsion Laboratory folded in 4 new transit observations of K2-18b on top of everything that had come before, gathering more light than anyone had yet brought to bear on the question. They confirmed the methane. They found decent evidence for carbon dioxide, but for dimethyl sulfide they found only a marginal signal, below 2 sigma, which in the language of their statistics was not enough even to call it evidence. Their conclusion was blunt and careful at once. There was no conclusive evidence for dimethyl sulfide. The signal that had caused so much excitement had, in their more complete analysis, faded toward nothing. No one expects a signal to grow fainter when you gather more light, and yet that is precisely what happened here. A team led by a scientist named Raphael Luque at the University of Chicago took the fuller approach of analysing all of Webb's instruments together, the short, the middle, and the long infrared bands all at once, across the whole span of the light, and when they did that, they too found insufficient evidence for dimethyl sulfide or its cousin. What is more, they pointed out that a simpler explanation could account for much of what had been attributed to the exotic sulfur molecules. A far more ordinary gas, ethane, a simple hydrocarbon, could produce features in that part of the spectrum too, and ethane requires no life at all. It is the kind of molecule you would expect in a hydrogen-rich atmosphere as a matter of course. Why reach for the smell of an alien ocean, they asked in effect, when a plain and expected molecule fits the data at least as well? Then came a result that cut even deeper, and it came from 2 scientists named Louis Wellbanks and Matthew Nixon. They noticed something about how these analyses were done. When you search a spectrum for molecules, you have to decide ahead of time which molecules you're going to allow into your model. The original analyses had considered a fairly small set, around 20 possible molecules. Wellbanks and Nixon widened the net. They let the model consider around 90 possible molecules instead of 20, a much fuller list of the things that might plausibly be there. And when they did, something troubling happened. More than 50 of those 90 molecules got a statistical hit. The data seemed to want more than 50 different molecules, all at once, which cannot possibly all be real. and Wellbank's put the problem into a single sharp question that has stuck with me ever since I first read it. When you detect everything, he asked, did you really detect anything? When your method finds 50 molecules in a spectrum that can hold only a handful, then the finding of any one of them, including dimethyl sulfide, loses its meaning. Under their broader analysis, they wrote, the claims of a potential biosignature simply vanished. At Oxford, a scientist named Jake Taylor ran a deliberately simple, basic statistical test on the raw data, stripping away the elaborate modelling to ask the plainest possible version of the question, and found no strong evidence for any biosignature at all. And then a team led by a scientist named Kevin Stevenson published a paper with a title that left little doubt about its conclusion. K2-18dB does not meet the standards of evidence for life. They applied a formal framework that astrobiologists had developed precisely for moments like this, a checklist for how confident you are allowed to be about a claim sign of life, and they walked K2-18b through it, and they found it wanting at nearly every step. The mid-infrared spectrum, they argued, was highly susceptible to unresolved instrumental effects. Different reasonable choices about how to bin and process the data gave different answers about what the atmosphere contained. And in the great majority of their own analyses, using their preferred way of handling the mid-infrared data, no dimethyl sulfide or dimethyl disulfide appeared at all. Their most cutting phrase was that red noise, rather than a genuine astrophysical signal, plagued the mid-infrared data. Red noise is a particular kind of correlated wobble in a measurement that can drift and cluster in ways that mimic a real feature. And their fear was that the whole signal, the possible smell of the alien ocean, might not be coming from K2-18b at all. It might be coming from the telescope itself. No one predicts that the smell of an alien ocean might turn out to be the faint warmth of a machine, but that is one of the possibilities honestly on the table tonight. Sit with the strangeness of that for a moment, because it is genuinely one of the stranger truths of this whole affair. The mid-infrared instrument on Webb works at wavelengths, where the telescope's own faint warmth matters, where every subtle quirk of the electronics and the optics must be carefully accounted for, and where an unmodelled instrumental effect can leave a mark in the data that looks, to the untrained analysis, exactly like a molecule. So the entire debate, when you strip it down, is about whether a faint dip in a graph, a slightly lower count of photons at certain infrared colours, is a molecule in an alien sky, or a whisper of imperfection in a machine floating 1,000,000 miles away. The difference between we may have found life in the universe and the telescope made a small noise, in the end comes down to a handful of photons and how you choose to read them. No one expects the most consequential question in the history of science to hinge on the arcane details of instrument calibration. But that tonight is exactly where it hinges. And it hinges too on choices that sound almost absurdly small when you first hear them. When the raw data comes down from the telescope, it does not arrive as a finished spectrum. It arrives as a flood of individual measurements, and before you can read it, you have to process it, to group the measurements together into bins across wavelength, to decide how to clean up the noise, to choose which of several competing software pipelines to run it through. And here is the unsettling part. Different reasonable choices give different answers. One team, using one pipeline and one way of binning the data, finds a hint of dimethyl sulfide. Another team, using a different pipeline and a different binning, finds nothing. The same photons, gathered by the same mirror on the same nights, yield the smell of an alien ocean in one analysis, and empty silence in the next, depending on human decisions about how to slice the numbers. There are names for these pipelines, unlovely technical names, and the fact that the answer depends on which one you pick is, to the skeptics, the loudest alarm bell of all. A real signal, they argue, ought to survive any reasonable way of processing the data. A signal that comes and goes depending on your bookkeeping is a signal you cannot yet trust. And so, the discovery of life in the universe might ultimately be settled, not by a dramatic moment of unmistakable alien contact, but by a committee of astronomers arguing, patiently and rigorously, over which binning scheme to apply to a 6-hour dataset from a telescope orbiting a point in space 1,000,000 miles from Earth. The universe, it turns out, is stranger and more procedural than anyone imagined, and this is not the first time. There is a cautionary tale that hangs over this entire field, and every scientist involved in the K2-18b debate carries it in the back of their mind. In the September of 2020, a different team announced that they had detected a gas called phosphine in the clouds of Venus, a gas that, like dimethyl sulfide, was thought to be difficult to make without life. The announcement made headlines around the world. Life, on our own sister planet, hiding in the clouds, and then, over the following months, other teams reanalyzed the data, and the signal began to dissolve. Independent analyses could not reproduce it. Careful statistical work suggested that the apparent detection had been, at least in large part, an artifact of the way the data had been processed, a feature that came from the analysis rather than from the clouds of Venus. The phosphine claim did not entirely vanish, and its story is still debated in quieter corners, but it stopped being a discovery, and it became a lesson, a permanent reminder to everyone in the field of how badly you can want something to be true, and how a noisy signal will happily give you what you want if you're not merciless with yourself. Every scientist arguing over K2-18b remembers Venus. It is why the skeptics are so fierce, and why the careful ones, including Madhusudhan himself, are so careful. I want to pause here, in the middle of all this doubt, and say something about what you're actually watching when you watch this argument unfold, because it would be easy to hear all of this and feel disappointed, as though the whole thing were falling apart, as though the beautiful story of the alien ocean were being taken away. But that is not quite what is happening. What you are watching is science doing the thing it is supposed to do, and almost never gets credit for. You're watching a field of people, many of whom would love more than anything to be the ones who found life, deliberately and rigorously trying to prove themselves wrong. The reanalyses, the skeptics, the fierce arguments over binning schemes and pipelines and sigma levels. This is not the failure of the process. This is the process. This is exactly how you avoid fooling yourself about the most important question you could ever ask, and there is something deeply reassuring in it, something that should let you rest easier rather than harder, because it means that if the day ever does come when someone says we have found life, and the claim survives this gauntlet, then it will be true. It will have earned every ounce of belief. The very fierceness of the doubt tonight is the thing that will make the eventual answer, whatever it is, worth trusting. By the end of tonight, I hope that reassurance sits inside you as gently as the story itself, and it is worth being fair to the hopeful side too, because the debate is not settled in the skeptic's favour either. It is genuinely open. Madhusudhan and his colleagues have their own responses to the criticisms, their own arguments about why their analysis holds up, their own view that the fuller picture, the methane and the carbon dioxide and the missing ammonia and the possible sulfur gas, still points toward a Hycean ocean world more naturally than toward any of the alternatives. The carbon dioxide, for instance, in the more complete July 2025 analysis, actually came through more strongly than before, at a confidence high enough to take seriously, even as the dimethyl sulfide faded. And whether the planet is truly a Hycean ocean world at all is its own separate live argument, with careful scientists on multiple sides. Some models say the data are better explained by a gas-rich mini-Neptune with no habitable surface anywhere, a world where the hydrogen envelope goes down and down into heat and pressure, with no ocean at the bottom, and where the methane comes not from life but from ordinary deep chemistry, cooked up in the hot interior and mixed upward. Other models raise the possibility of a magma ocean world, a surface not of water but of molten rock. Each of these fits the available data reasonably well, and each requires you to imagine K2-18b as a completely different kind of place. So the ocean itself, the world-wrapping sea I asked you to picture at the start of the night, is not a fact. It is one interpretation among several, the most beautiful one perhaps, but not the only one the numbers allow. There is even an argument about the very foundations. Some of the original excitement rested on the idea that the amount of methane and the absence of ammonia and the levels of carbon dioxide all pointed specifically toward an ocean beneath a hydrogen sky. But for each of those clues, careful people have offered a gentler, more ordinary reading. The methane might come from deep thermochemistry rather than from life. The missing ammonia might be depleted by chemistry high in the atmosphere, rather than dissolved into a sea. The carbon dioxide might be present, or it might depend on exactly which team reduced the data, since at least one independent analysis found no statistically significant carbon dioxide at all. Every single clue, taken alone, has an innocent explanation. The hopeful case has always rested not on any one clue, but on the way they seem to line up together, all pointing the same direction. And the skeptical case is, in essence, that when you look hard enough, they stop lining up, and each clue drifts back toward the ordinary. Take the methane, for instance, since it is the clue everyone agrees is really there. On a world with an ocean beneath a hydrogen sky, one line of reasoning goes, the amount of methane detected is high, higher than you might expect from ordinary chemistry alone, and on Earth a great deal of methane is made by life. So a high methane level on a possible ocean world is at least suggestive, but the counter-argument is patient and plausible. In a deep, hot, hydrogen-rich atmosphere loaded with heavy elements, methane can be cooked up by plain thermochemistry in the hot interior and mixed upward into the visible sky. No biology required at all. Both stories fit the methane. The same is true of the carbon dioxide. In the more complete analyses, carbon dioxide comes through reasonably well, and the pairing of carbon dioxide with methane can be read as a kind of chemical imbalance that life sometimes drives. But at least one independent team, reducing the data their own way, found no statistically significant carbon dioxide at all, which means that even this clue may depend on whose hands processed the numbers, and the missing ammonia, the absence that was read as a sign of an ocean dissolving it away, can also be explained by chemistry high, in the atmosphere breaking the ammonia down, with no sea required. Clue by clue, the same pattern repeats. Each one has a living explanation and a lifeless one, and the honest truth is that we cannot yet tell which is right. That is not a comfortable place to stand, but it is where the evidence actually leaves us tonight. That is where the debate stood, and largely still stands. A signal that some see and others do not. A planet that might be an ocean world or might be a lifeless ball of gas. A molecule that might be the smell of an alien sea, or might be a whisper of ethane, or a quirk of an instrument, or nothing at all. And into that already tangled picture, in the January of 2025, came a new discovery that complicated everything further, from a direction no one in the exoplanet world had quite been watching. Because a different group of scientists working on a completely different problem, in a completely different part of the sky, found dimethyl sulfide in a place where there is no ocean, no planet, and no possibility of life whatsoever. Tonight we're going to travel there next, to the coldest and emptiest place in the whole story, and it is there that the biosignature itself begins to come apart. Let me take you there, because it is one of the eeriest and most beautiful findings in this whole story. Near the centre of our own galaxy, some 26,000 light-years from Earth, there is a vast cold cloud of gas and dust, one of the great molecular clouds that drift through the Milky Way. Astronomers give these clouds unlovely catalogue names, and this one is called G plus 0.693. It is an enormous, sprawling region of interstellar material near the galactic heart, and it is a place of extremes. It is bathed in harsh radiation. It is swept by cosmic rays. It is bitterly cold in places and shocked and heated in others. Nothing lives there. Nothing could. There are no planets in it, No oceans, no algae, no bacteria, no biology of any kind. It is simply gas and dust and starlight, the raw material from which stars and worlds are slowly born. And in that cloud, using radio telescopes on the ground, a team of astronomers based in Madrid detected the unmistakable radio fingerprint of dimethyl sulfide, the same molecule, the smell of the sea, the supposed signature of life, found drifting in a cold cloud at the centre of the galaxy, where there is no sea to smell and nothing alive to make it. They measured its abundance carefully, and they compared it to other molecules in the same cloud, and they found that the ratio of dimethyl sulfide to other simple compounds matched, almost exactly, the ratio that had been measured in the material of a comet in our own solar system, a comet called 67P, which the European Rosetta mission had visited and studied up close a decade earlier. A comet is a dirty ball of ancient Hycean rock, a leftover from the birth of the solar system, and dimethyl sulfide had been found in its material too, floating up from the frozen remains of the cloud our own sun was born from, 4.5 billion years ago, long before Earth had any oceans at all. Let me linger on that comet for a moment, because it makes the point in a way that lodges in the body. The comet is called 67P, and a decade ago the European Rosetta mission chased it down and flew alongside it for 2 years, and even dropped a small lander onto its surface. The comet is a dark, lumpy thing about 2.5 miles across, a mountain of dirty ice and rock left over from the very birth of the solar system, drifting on a long, slow orbit through the cold. And Rosetta carried instruments that could, in effect, smell the thin haze of gas the comet gave off as it warmed near the sun. Among the molecules in that haze, scientists later found the fingerprint of dimethyl sulfide, the smell of the sea, rising off a lifeless lump of primordial ice that had formed 4.5 billion years ago, before the Earth's oceans existed, from the same cold cloud that made our sun. There is no sea on 67P. There never was. And yet the molecule was there, carried down from the birth cloud into the body of the comet, waiting in the ice for billions of years. And think about the instrument that heard the interstellar version of it. To detect dimethyl sulfide in that cloud near the galaxy's centre, the team used a great radio dish in Spain, a 40-metre telescope in the province of Guadalajara, pointed at the heart of the Milky Way, 26,000 light-years away. The molecule's signature came in not as visible light, but as faint radio waves, a specific pattern of frequencies that only dimethyl sulfide produces, arriving after a journey of 26,000 years across the galaxy to land in a radio receiver and be recognized in a laboratory in Madrid. The same molecule that makes the low-tide smell of a harbour on Earth, sung across the galaxy in radio, from a place where nothing lives. No one predicts when they walk down to the sea and breathe in that briny air, that the very same molecule is drifting through the cold clouds at the centre of the galaxy, made by chemistry alone. Put those two findings together, and the conclusion is hard to escape. Dimethyl sulfide can form without life. It forms in the cold clouds between the stars, assembled by nothing but chemistry, by atoms meeting on the surfaces of dust grains and joining together in the dark. It formed in the cloud that made our sun. It rode down into the comets. It drifts near the centre of the galaxy in a place where nothing lives. The team who found it wrote it plainly. Dimethyl sulfide, they concluded, can be formed abiotically, without life, efficiently, even in the earlier stages of a star's birth. And with that one sentence, the single most important assumption behind the K2-18b excitement, the idea that this molecule means life, was thrown into serious doubt. There is something almost dizzying about it when you let it sink in. The one molecule that scientists had pointed to and said, "Only life makes this," was found in the most lifeless place imaginable. Cold gas and dust between the stars. The smell of the ocean drifting through the void, with no ocean anywhere for trillions of miles. And it means that when Webb catches the faint fingerprint of dimethyl sulfide in the sky of K2O18b, even if that signal is completely real, even if every skeptic's worry about instruments and noise turns out to be unfounded, the gas itself would no longer be proof of anything living. Because now we know the universe can make it in the dark, alone, without a single living cell. No one expects the signature of life to be found in a place where nothing could ever live, and yet there it was, drifting near the heart of the galaxy, and it did not stop there. In laboratories on Earth, chemists took the kinds of gases that might fill a world like K2-18b, mixtures of methane and hydrogen sulfide, and they shone ultraviolet light on them, mimicking the way starlight would fall on the upper atmosphere of such a planet. And out of that lifeless mixture of gas and light, dimethyl sulfide formed, along with its cousin, dimethyl disulfide. No algae, no bacteria, no ocean, just gas and light and chemistry, making all by themselves the very molecules that had been offered as the signature of life. And the modelers who study K2-18b's own atmosphere found the same thing in their calculations. In a massive hydrogen-rich atmosphere of the kind K2-18b probably has, these sulfur molecules might well form through ordinary photochemistry, cooked up by the star's own light acting on the planet's own air, with no biology involved at all. This is what scientists mean when they talk about the requirements for a good biosignature, and it is worth stating plainly, because it is the quiet lesson at the heart of the whole night. For a molecule to be a reliable sign of life, 3 things have to be true. It has to be made in large amounts by living things, so there is enough of it to see. It has to be hard to make without living things, so that finding it means something. And it has to be detectable across the vast distances between the stars, so that we can actually catch it. Dimethyl sulfide passes the first test easily. On Earth, life makes floods of it. It passes the third test too, since Webb can, at least arguably, catch its fingerprint across 700 trillion miles. But the second test, the crucial one, the requirement that it be hard to make without life, is exactly the test that the discoveries of 2024 and 2025 have called into question. In the cold clouds between the stars, in the ice of comets, in the glare of ultraviolet light on a hydrogen sky, the universe appears to make dimethyl sulfide all on its own. And a molecule that the universe can make on its own is not, by itself, a fingerprint of life. It is just a molecule. Now, the scientists who found the interstellar dimethyl sulfide were careful, as good scientists are, not to overstate their own result either. They did not claim that their discovery kills the idea of dimethyl sulfide as a biosignature forever. What they showed is that context matters enormously. Finding the molecule is not enough. You have to ask how much of it there is, and what else is there alongside it, and whether the amount and the mixture make more sense as the product of life or as the product of ordinary chemistry. It may still be that a certain abundance of dimethyl sulfide in a certain kind of atmosphere alongside a certain suite of other molecules would point toward life more strongly than toward chemistry. The molecule is not useless as a clue. It is just no longer a proof on its own. By the end of tonight, that word, context, may be the single most important thing you carry away from all of this. And that is a more subtle and more honest place to stand than the simple, thrilling headline that a chemical made only by living things had been found in an alien sky. So where does that leave K2-18b tonight, as you lie there in the dark? It leaves it exactly where science so often leaves us, at the edge of knowing, in the honest fog of an unfinished question. We have a planet that might be a world-wrapping ocean beneath a hydrogen sky, or might be a lifeless ball of gas, or might be a world of molten rock. We have a molecule that might be present in its atmosphere, or might be a ghost in the machine, and that even if present might come from life, or might come from the plain chemistry of gas and light. We have a signal at 3 sigma from one team and below 2 sigma from another, a signal that appears and vanishes depending on which careful hands process the numbers. We have the smell of the ocean hanging over an alien sea that may not exist. It is, when you lay it all out, one of the most beautifully unresolved questions in all of science. And no one predicts, when they first hear the exciting headline, just how deep and how patient and how genuinely uncertain the real story underneath it is. Tonight we're going to let that uncertainty be, without needing to resolve it, the way you let a question rest in your mind as you fall asleep. What would it take to know for sure? The scientists have an answer to that, and it is a humbling one. To push the detection of dimethyl sulfide on K2-18b up to the level of a real discovery, or to rule it out definitively, one independent group estimated that Webb would need to gather something like 26 more transits of the planet with its mid-infrared instrument. 26 more passages of the planet across its star, each one gathered over hours, each one demanding a precious slice of the most sought-after telescope time in existence. A telescope for which the entire astronomical community competes fiercely for every hour. 26 more transits is an enormous investment, and whether it will ever be spent on this one planet, when there are thousands of other worlds to look at, is itself an open question. So it is entirely possible that we will not settle the case of K2-18b for years, and possible that the definitive answer will have to wait for a future telescope not yet built. This is not a story that resolves by the end of the night. It is a story that resolves, if it ever does, by the end of a career or by the end of a generation of instruments. And there is a discipline that astrobiologists have built for exactly these moments, a kind of ladder of questions you must climb before you are allowed to claim you have found life, and it is worth walking up its rung slowly because it shows you just how far K2-18b still has to go. The first question is simply, have we detected a genuine signal at all? Something real in the data rather than an artifact of the instrument? That question alone, as we have seen, is fiercely contested for K2-18b. The second question is, if the signal is real, have we ruled out every way it could be produced without life? And here the interstellar dimethyl sulfide, the comet, the laboratory photochemistry, all of them stand in the way, because they show the molecule can be made without life at all. The third question is, does the planet's environment actually support the interpretation we are drawing? Is there really an ocean and a sky where this story could unfold? And that too is debated, since the ocean itself is only one model among several. The fourth question is whether the amount of life we would need to invoke is even plausible, given what we understand of biology. And the fifth, the humblest of all, is whether the signal could simply be contamination, something from Earth or from our own instruments masquerading as a distant world. To claim life, you must answer all 5, in order, convincingly. And K2-18b, tonight, answers not one of them beyond doubt. That is not a failure. It is simply where an honest search stands when it is still early. By the end of tonight, I hope that ladder feels less like a wall and more like a staircase, one that humanity has, for the first time in its history, actually begun to climb. There is a precedent for exactly this kind of moment, and it happened not on a distant exoplanet but on a world close enough to see with the naked eye, the planet Venus. In the autumn of 2020, a team of astronomers led by Jane Greaves at Cardiff University announced that they had detected phosphine in the clouds of Venus, a gas that on Earth is produced almost exclusively by biological processes. The announcement was enormous. Headlines around the world declared that scientists had possibly found signs of life on our nearest planetary neighbour. The paper passed peer review. It was published in Nature Astronomy, one of the most prestigious journals in the field. And for a few weeks it seemed as though the search for life had made a sudden, astonishing leap. Then came the reanalysis. Other scientists went back to the raw data and found a calibration error in the telescope readings. When the error was corrected, the apparent strength of the phosphine signal collapsed. A different team reprocessed the same data and found a signal, but a much weaker one, uncertain enough to be questioned. A third team examined the chemistry and argued that the sulfur dioxide in Venus's own atmosphere might mimic phosphine's fingerprint at the specific wavelength where the detection had been claimed. Papers came quickly, arguing both ways, and the scientific community split into camps. 3 years later, the question of whether Venus has phosphine at all is still genuinely contested. The original detection has neither been confirmed nor definitively ruled out, and in that fog of uncertainty, the planet that seemed on the verge of answering the question of life continues to drift through our sky, orange and opaque, holding its answer behind its clouds. What the Venus episode teaches is something that K2-18b is now teaching again. No one expects the first announcement of a biosignature candidate to be the discovery. It is the beginning of a process, the opening bell of a long and rigorous examination that may take years and involve dozens of independent teams before it settles into something resembling certainty. The signal emerges from the data, and the community forms around it, not to kill it, but to test it, to find out what it really is. Some signals survive that testing. Most do not, or at least not in the form they first appeared, and the ones that do survive are the ones that have earned the right to be called real. No one expects the answer to come from the first pass of the data. No one predicts that life, if it is there, will announce itself without ambiguity. But for the first time in the history of the question, we are asking it with instruments that might actually hear the reply. K2-18b is in the early stages of exactly that process. The signal will be pushed and pulled by teams across the world for years, reprocessed through different pipelines, tested against new instrument calibrations compared to fresh observations gathered in future cycles of telescope time. More transits will be gathered. New models will be built and torn apart. Whether the detection survives that gauntlet, what form it takes if it does, whether the Hycean ocean and the sulfur chemistry will one day be confirmed or will dissolve under scrutiny, these are questions that belong to the years and decades ahead. But the fact that the process is happening at all, and happening with an instrument as extraordinary as the James Webb Space Telescope, aimed at a world as genuinely strange as K2-18b, means that we are closer to having a real answer than any human generation has ever been. Not close enough to know tonight, but close enough to feel the shape of knowing, to sense that the answer is somewhere in the reach of the instruments we have built or will build, somewhere in the careers of the scientists now running the analyses, somewhere in the future of a species that has, for the first time, learned to read the chemistry of other worlds. And K2-18b is not the only world on that staircase. Some 40 light-years away, closer to home than K2-18b, there is a small red dwarf star with a wonderful name, TRAPPIST-1, and around it circle 7 rocky worlds, packed close together, 3 of them sitting in the habitable zone. That system is the other great hope in the search for life, and Webb has been turning its golden eye toward it too. So far the results there have been quieter, and in their own way instructive. For some of those TRAPPIST worlds, Webb has ruled out the presence of thick atmospheres, finding bare hot rock where some had hoped for air. For others, the question is still open, the data still consistent with many possibilities. There is no headline there, no whisper of a biosignature, just the patient narrowing of what might be. And that quiet, careful work is exactly what the search looks like most of the time. Not the thrill of a possible ocean full of life, but the slow ruling out of possibilities, world by world, atmosphere by atmosphere. K2-18b is loud because of its sulfur signal, but the real texture of the search is the long, quiet examination of dozens of worlds, most of which will turn out to be lifeless, until one of them, someday perhaps, is not. And yet, and this is where I want to carry you as the night deepens, even in all that uncertainty, something real has happened. Something that does not depend on which way the K2-18b question finally falls. Because whatever K2-18b turns out to be, the fact that we can even ask this question seriously with real instruments and real data is brand new in the history of our species. For almost all of the 300,000 years that human beings have existed, the question of whether any other world was alive was simply unanswerable. It was a thing for myth and dream and prayer, not for measurement. Our ancestors looked up at the same stars you can see tonight and wondered, and had no way at all to find out. We have had radio telescopes for less than 100 years. We have known for certain that other stars even have planets for only about 30 years. The first planet around another sun-like star was confirmed in 1995, within many living memories. A single strange world that proved at last that we were not alone in having worlds, whatever else we might or might not be alone in. And now, 3 decades later, we have found around 6,000 of them, 6,000 confirmed worlds circling other stars, and we have gone from merely detecting them to weighing them, measuring their sizes and their masses, and now, with the golden mirror at L2, reading the chemistry of their skies. K2 18b may or may not be alive, but the ability to walk up to a planet 700 trillion miles away and ask, in the language of chemistry, is something breathing there, and to get back an answer detailed enough to argue about, that ability is one of the quiet miracles of the age you happen to be alive in. 400 years ago, Galileo pointed a small tube of glass at Jupiter and saw 4 points of light moving around it, and it changed the world. Tonight, a golden honeycomb a million miles from Earth reads the exhalations of alien atmospheres. You're living in the century when we learn to smell other worlds. By the end of tonight, I would rather you fell asleep marvelling at that than fretting over which team was right. Whether or not any of them turn out to be alive, that is a thing worth lying awake just for a moment to marvel at, before you let it carry you down into sleep. There is a way of thinking about all of this that reaches back to a lunchtime conversation in the summer of 1950, when a physicist named Enrico Fermi, walking with colleagues to lunch, is said to have asked a simple, haunting question about the possibility of alien civilizations. Where is everybody? The galaxy is old, he reasoned, and vast, with hundreds of billions of stars, and if life and intelligence were at all common, the galaxy should be full of them, should have filled itself many times over across the eons. And yet the sky is silent. We hear nothing. We see no one. Where then is everybody? That question has echoed ever since, under the name of the Fermi paradox, and K2 18b touches it in a way that is worth turning over slowly as the night gets late. Because suppose, for a moment, that the hopeful reading is right after all. Suppose that beneath that hydrogen sky there really is a world-wrapping ocean, and that ocean really is thick with living things, microbes drifting by the uncountable trillion, exhaling their dimethyl sulfide into the air until it builds to those staggering concentrations. If that is true, then think about what kind of life it is. It is not intelligent. It builds nothing. It sends no signals. It does not know that it exists, and it certainly does not know that we exist, or that a golden mirror a million miles from a small blue planet is watching its sky and wondering about it. It is ocean life, microbial life, the kind of life that filled Earth's own seas for billions of years before anything crawled onto land. And it may be the most common kind of life in the whole galaxy. Not the shining civilizations of science fiction, broadcasting across the stars, but silent oceans full of microbes on sub-Neptune worlds. Worlds that are, remember, the most common kind of planet there is. And if that is the shape of life in the universe, then it offers one quiet answer to Fermi's question. Maybe the galaxy is not empty at all. Maybe it is teeming with life, ocean after ocean of it, on world after world, and the silence Fermi noticed is simply the silence of a universe full of things that cannot speak and would not know how. Life, in this reading, is not rare. It is everywhere. But it almost never becomes anything that looks up or wonders or reaches out. It stays in the water, in the dark, exhaling its chemistry into a hydrogen sky for billions of years, and never once crosses the enormous distance between being alive and asking what it means to be alive. If that is true, then we are not the lonely exception to a dead universe. We are the strange exception to a living one, Not alone in being alive, but perhaps very nearly alone in knowing that we are. No one predicts, when they first ask where everybody is, that the answer might be that everybody is quietly floating in oceans that will never know the question. I find that thought oddly comforting at the end of a night like this one, and I offer it to you to hold as you drift. The universe may be crowded with quiet life, oceans exhaling under distant red suns, and we may be among the very few who ever learn to look up and notice. That does not make us less alone in one sense, and it makes us far less alone in another, and both of those things can be true at once, the way so many things in this story are two things at once. A signal and a noise, an ocean and a gas cloud, a discovery and a doubt, the smell of the sea and no sea at all. And there is one more asymmetry worth resting on, because it is the strangest and gentlest of them all. If we do detect the fingerprint of life on K2-18b, that will never quite prove that life is there, because as we have seen, every fingerprint has an innocent explanation, and certainty is hard to reach across 700 trillion miles. But the reverse carries a strange weight. If we look hard enough, and long enough, and the fingerprint is not there, that near absence would tell us something almost as profound in the other direction. That this most promising of worlds is, after all, only chemistry. And whichever way it falls, the little world in Leo will have taught us how to ask the question of every world that comes after it. It may be that K2-18b is not the planet where we find life at all, but the planet that proved the search was real. The way that First World found around another star in 1995 was not itself remarkable, except that it proved there were worlds to find. K2-18b may be remembered not as the answer, but as the place where humanity learned, finally, how to listen to the sky for the sound of something breathing. So let the night carry you now, gently, towards sleep, and let me leave you where we began, at the edge of the water. Somewhere, 124 light-years away, 729 trillion miles, from the warm dark room where you're lying, a small red star burns low and slow in the constellation Leo, an ember of a sun that has been glowing for over 2 billion years and will glow for many billions more. And around it turns a world more than twice the width of your own, wrapped in a sky of hydrogen, and beneath that sky perhaps an ocean without shores, hundreds of miles deep, dark and still under a dim red light that never rises and never sets. That is the planet. It has been there all along, indifferent to our arguments, keeping whatever secret it keeps, whether that secret is an ocean full of quiet life, or only the plain and lifeless chemistry of gas and light. It does not know we are watching. It turns, and the smell of the sea, or the ghost of that smell, rises into its sky. And there is the question, the one we have carried all night, the one that has stood at the threshold of the most consequential discovery our species could ever make, unsure still whether it is knocking or whether it is only the wind. Is something alive out there? Not intelligent, not reaching for us, not even aware, but alive, breathing its chemistry into an alien sky, the way the algae of our own oceans have breathed for 1 billion years. We do not know. The signal fades and returns. The scientists argue gently and fiercely over binning schemes and sigma levels and the faint warmth of a distant machine, and they do the hard, honest, patient work of refusing to believe the thing they most want to be true until it earns their belief. And that work will go on, transit by transit, telescope by telescope, long after tonight, until one day, maybe, the answer comes, not as a shout or a signal, but as a small line on a graph, drawn at last with enough certainty to trust. And there, at the end of it all, is you, lying in the dark, your breathing slowing, your thoughts loosening their grip, drifting now toward the edge of sleep, the way that faraway ocean drifts under its red and unmoving sun. You do not have to solve it tonight. You do not have to know whether the smell of that distant sea is life or chemistry, whether the door is opening or the wind is only rattling it. You only have to let the question be what it is, one of the most beautiful unfinished questions there is, and let it rest beside you, unhurried, the way the great slow processes of the universe are always unhurried, taking billions of years to make an ocean and a few more transits to know whether anything is swimming in it. The golden mirror will keep watching. The little world will keep turning. And the answer, whatever it is in no hurry at all, and neither now are you. Sleep well tonight. Somewhere out in the dark, under a dim red sun, an alien sea may be breathing, and we are only just now learning how to listen. Good night.